sorry that you waited. So there are some people here with me, and I hope that you will hear us good also in the recording. I'm opening the presentation, and I'll share the screen within 1 second. And I must say that the presentations are, I think, a very good application of the basic idea. Can you also please close in? Okay. There are 2 people who wanted to talk with me and I don't see, so I'll just write in the okay. I'm here and API to console, and please log in or come to speak face to face. Okay, it takes really a lot of time. So maybe meanwhile, I don't know, would you like just to start asking the questions until I open the presentation? Okay, okay. Great.
Who wants to start?
Go, Irene.
Okay. Should I share my screen or?
Yeah, I'll open the, so
Oh, wait, because I'm so confused. I can't hear you, but I know you.
you can hear me.
Yes.
Okay, so you can share the screen.
I'll share the question in question.
Hi.
My computer doesn't have access. Okay, my question is just about question 2
Yeah,
of the project, section C,
right.
where we
Okay.
have to use the formula to create a model of the neuron.
Yeah,
And we use the kernel, the DFT that we found with the white noise
right.
complementary experiment.
Yeah,
The stimulus we combined is first, the main, no, the SFT is the SFT from the main experiment, is not the
Yes.
SFT from the complementary experiment. And the baseline rate should be the rate of the main experiment's neuron,
yes.
the DC offset. Okay. The problem with that is that when we do that conceptually, I expect that I get a model that looks like the rate of the first experiment. And it's absolutely trash. Like, it looks terrible. Wait, where is it?
Mhm.
This is like even the range. This is how it should look like. How the rate of the first main experiment looks like. And this is my estimated model done with the convolution and the formula. And I'm not sharing on Zoom, but basically I have a very bad noisy estimation.
Okay, can I ask you to try something? Maybe try to add the STA, not of the white noise, but rather of the main experiment.
In the kernel?
Yeah,
So the kernel should not be made with the STA.
it should, it
Okay.
should, but let's check. It should be made by the STA of the white noise, but I was also looking at the STA result, and I was wondering to myself, the STA of the noise looks much more noisier, right, of the white noise, if you plot it,
This is
or
it.
is it about the same? Can you
It's-
tell me?
So the white noise, the STA
Ah.
with the white noise looks like this for me.
Yeah,
And
okay,
then of course the kernel is the same more or less. the
yes,
kernel
yes,
that we create.
of course,
But when I use this kernel, this basically the kernel that I obtained with the SDA from the noise.
Yeah, so it looks okay, but how does the SDA of the main experiment look like?
I haven't plotted it. Oh, no, I did, sorry.
Because I think this is the
Sorry.
first question.
This is it, yeah.
Ah,
sorry.
no, so it's okay.
Yeah,
No, you should have used the white noise. This one should work. I'm thinking to myself, maybe it has to do something with the convolution of the firing rate or something like that.
okay, like.
I got the same result actually, and I wanted to ask about because
Because, wait a minute, can you please go up?
So the,
This is how the result that I get really looks similar to this one.
but this is from the second, this is from the complementary neuron, this is the optimal.
Yeah, yeah.
Okay,
Oh, so maybe try, you know what, try not to, maybe try not to estimate your model with the main experiment, but rather with the complementary.
and it's still trash. I tried both, and it's still like horrible. I don't know why. Like I
Yeah.
tried with the opposite.
just tell us what should we expect to get? Maybe this is the right result.
It looks about the same, but it's more convolved.
It's
It,
supposed
it,
to look about the same to what?
to the, let me double check it with my answer key.
Like to your optimal firing rate essentially that you got initially, so it should look the same as the.
Yeah, it
something
looks
like this,
almost the same like this one.
like this is your optimal firing rate, but not at all.
It doesn't.
Like, and I tried using the DC offset from the complementary and the noise from the complementary, and it's still very bad, like, the estimation ultimately doesn't estimate properly.
It's really strange because when I did it, I remember what is your estimation? Can you
This
please
is
tell me?
the estimation
In
with-
blue?
in blue, and this is my plot of what the main neuron response is.
Can you try to convolve your estimation
Okay,
to smooth it?
okay, yeah, okay. To see if but even my thing is also the scale of it is very off, right?
Yeah, this is one of the strange things about it.
Mhm.
And I
Okay.
think where could the scale come from? Because maybe there is something with zeros.
That might be.
For example, maybe you use the zero tagging or.
Divide by the side or something, you got
Okay.
a second to me.
Yeah, I tried, actually, yes, I think I tried another section, I tried to normalize the kernel, and then the firing
Yes.
rate went from -100 to 200 hertz. But this is supposed to be.
This is
acid.
still very high.
Yeah, it's not
Okay.
right, yeah, that's right with the right DC offset, like it should be more or less, yes, it should be more or less around, here I have it, okay. So around the same, the right rate, but
Yeah.
still a mess.
But if you convolve it, try to
Okay.
convolve
To
it,
clean it,
Yes.
okay,
because what I see is like very, very fast fluctuations, which might come from the fact that the kernel looks like a kind of a very, right, your optimal kernel is very, very narrow.
Mhm.
And we will learn about it when we talk about filters and Fourier transform. And then you might have this effect since it is very, very narrow.
Mhm.
So you're just kind of adding problematic frequencies that are not there.
Okay.
So I think that this might be related.
Okay, and also normalizing the kernel.
Yeah.
Okay. Yeah, I need to. I'll-
Because I look at like the main, your main graph, when you look at it, it looks okay. It looks just very close to the firing rate in the complementary,
Mhm.
right?
But we have to compare it to the firing rate in the main, right?
To the firing rate in the main.
Because
Yeah,
right?
yeah.
Okay,
It
just to
should
make
also
sure.
work for the main. Yes, it's just given a stimulus, it should predict.
So
the neural response.
we expect that it just predicts the
Yeah.
neuron in general, like,
Yeah.
not, yeah.
So what I see is that only the fact that you have these edges, right,
Mhm.
at the kernel, I think this is what,
Yeah,
this what affects your, result.
okay, so just clean it.
Yeah.
And see if it looks better, and then.
Because
optimize
again,
it.
look at the main.
There's something.
Yeah, right?
Just a little,
It's just very, very noisy.
yeah.
So
Okay.
you just need to reduce the noise.
And we were comparing this to, what is it, the firing rate of the neuron, the first stimulus. the main-
It shouldn't matter because, right, the idea about the
Yeah,
model
it's
is that
supposed to-
given any stimulus, you can predict the outcome. So it doesn't matter if you add the main experiment or the supplementary one. Not supplementary,
The complementary.
the
yeah.
complementary,
Uh-huh.
yes. It shouldn't matter.
Okay, but still conceptually, we're constructing the model with the ST, the stimulus
Yeah.
from the main, and the DT, that's the kernel we got from the main.
Exactly,
Okay,
yeah.
all right, thank you. I'll look at next.
Can I ask something regarding this?
Yes,
So when we are calculating the linear kernel, the formula has the average firing rate multiplied by the STA with the white noise divided by the variance of the
Yes.
white noise.
yes,
So the average of the firing rate, is it okay if I average the firing rate of each of the responses of the complementary file?
I think yes,
Okay.
as far as I remember.
And the STA, what I understand from what Irene and Adia and the others, we should do it on the white noise, but if not, then we try on the red. But if we put on the white noise, that means that we are aligning with white noise in each of the responses that we have, which is the matrix, right?
Wait a minute, sorry, I'm just, I was just about to open the presentation, but I don't find the link, so sorry if someone can just send me. So,
Yes.
yes, just send me in WhatsApp. Sorry, so again, so you said that you aligned the noise,
White noise
yes.
in the responses, which is the
So you have the spike in activity, right?
yes.
Right,
the
yes,
matrix.
yes,
Okay, so we will do it for all of the rows in the matrix.
yes.
Okay. And the variance of the white noise is just the variance of the initial vector.
Yes,
Okay.
yes. You're welcome. Thanks, Julia. Julia or Christian? Christian. Right? Ah, okay.
Yeah.
Okay, so now I can open it. Right. Okay, and let's start first if anyone else has more questions about this specific
Yes, it's all about, my questions are.
Yeah, most of the questions.
Okay, so let's okay, got it. Let's go into more details. So I'll come back to the about the recitations and now,
The recitation are also from this, like it was just the part of the recitation about this
okay,
project,
okay,
but it was more conceptual rather than like a question about the.
okay, great. So I'm going inside, oh, Christian, because you're the first one.
I swear it wasn't mine. I put it in the recitation.
Okay, right, so we have this formula for the optimal kernel. And now how come normalizing the STA to firing rate and the equation that goes dt, the same thing?
Because this, like, in the steps, it says, no, and like, it's my problem on mathematics, it's like, it says normalizing the STA to firing rate.
Yes,
And then the equation goes STA times R divided by, like, I don't understand how.
Right,
those
it's
two
divided
ideas
by-
are the same.
so,
Because the formula is having the firing rate at the top in the numerator, so if you divide by the firing rate, then you are just eliminating this term.
Like,
wait a
what is-
minute, okay,
Which-
we need to,
No, did you say the linear camera? The formula is I divided by the lines. If you normalize by the time where you're dividing by time.
Yeah, you kind of say that it should have been the opposite because you kind of multiply. You need to get rid of the stimulus, right? So you'd expect that you'd divide by the STA and then you get rid of the stimulus and you have this R. Right, so I'm thinking about it. But the fact that you convolve with it, it doesn't matter because it's just multiplying with the moving window. So, like the basic idea that I write normalizing the STA to firing grade is the fact that we need to have at the numerator, right? This is the one on the top, the numerator. So we need to have a firing rate at the numerator, right? Because our model predicts the firing rate. So therefore, the problem is that we do not divide by the STA, right? The STA is a function of the stimulus. So it needs to be cancelled with the ST, with a given ST, right? Basically, okay.
Sorry.
So, 1 minute, I'll open the citation.
Like, I think I have a very conceptual question on like, what are we doing with the linear kernel? Like, I think I missed, like, I thought I was following it, and then when I went to do the project, I'm like, oh, okay, I don't
You
think
feel
it
that
fully
you
follows.
don't fully clear, yes. Right, okay, so let's look again at the model. So we have the model, right?
On the left
This,
page, yeah.
sorry. Right, so we have the model. Therefore, on the left, we have firing rate equals firing rate plus something that transforms the stimulus into firing rate, right?
Okay.
This is the idea. So now we need to ask ourselves, how do we transform the stimulus into firing rate? Okay, so we have to in the optimal kernel, in the DT, we must have at the numerator, we must have something which is related to the R, right? Because if it will be on the denominator, then it could not be by units equal to the right place, okay? So this is why the R is at the numerator. But now we need to ask ourselves, why do we have also the stimulus? STA is a stimulus, right? So why is the stimulus also in the numerator? Okay, and this is, now I'm trying to think about it. Thank you. So can I ask you to try to divide by the STA instead of multiplying in your project?
Yes.
Divide by the STA.
Okay. So when creating the kernel, you divide by the STA.
Yeah, instead of writing here multiplication, just try. I'm just wondering, maybe there is a mistake here in the formula.
Okay, so wait, because I don't have it written down. R times SDA divide, okay, so we divide by variance multiplied by the SDA?
Yes,
Okay.
try it. I'm just wondering, maybe this could fix everything.
Okay. But I
Because-
did clean it and it looks a bit better, by the way.
Yeah, yeah,
So maybe this.
it looks much closer.
Okay, so I'll try to.
But if not, I'm trying to think. So do you understand the problem now?
Yeah.
So we still, okay. Let's say that we have 2 units. One of them is the firing rate, right? Which is spikes per second. And in the stimulus, you have, for example, I can show you, yeah, on board, but let's try first to explain it, and if it's not clear, then I'll show it on board. So we have the units of firing rate, which is spikes per second, and we have the stimulus, which is, for example, volt or decibels, if it is a voice or something like that, right? So now what we want to do, we want to get rid of the stimulus units from the decibels or volts. So therefore, we don't want to multiply. We want to divide by the SDA. So now I'm wondering to myself, I fully understand why does the average firing rate is in the numerator, but I'm wondering whether there is a mistake and the STA of T should have been at the denominator.
Yeah.
Okay, is that more clear now?
Yeah, because if you have SCA for the denominator, and if
Yeah.
you multiply by the stimulus, it just agrees.
Exactly. So this is what I'm wondering, but I fully remember that I had this discussion in previous years. And I remember that we left it like this because otherwise it's not working. So I'm really trying to get remembered why is it like this. So is it okay? I need to look a bit in the literature. So if someone can send me an email, if you can just send me the question again in email, and I'll just write a response, a full response regarding the nets.
But the unit of measure of variance, it's the unit of measure of the stimulus square. So if you multiply this with the stimulus, it will.
Right, exactly. I think this is the reason, right? Because of the, right,
So the variance has to be.
yeah,
based on the ST of the
exactly,
stimulus. Yeah.
exactly.
Very
So the
good.
fact it is squared, this is why you have to have the stimulus on top. So, okay, so
Mhm.
we got it. So is it now more clear?
Yeah, and then my question is like, it looks arbitrary in the sense of like, oh, you're just putting things to cancel out the units. Like,
Yeah.
what is the theory behind those are the things that we're putting in the DT?
Ah,
control?
okay. So we understand why do we need the average firing rate, right?
Yes.
And now we ask ourselves, why do we need the STA and the variance,
Mhm.
right?
Yes.
So the STA is our way to say that we find the kind of the preferred stimulus,
Mhm.
right? Do you understand what I mean by that? STA it is a reverse correlation, so we are looking what is the relevant stimulus, the most preferred stimulus on the neuron. So the STA represents how to make the neuron work
Okay.
in a very simplistic way, right?
So, wait, the STA. Let me open my STA. So the STA, it's stimulus over time,
Right,
right?
yes.
How are you telling from that? Like, what is, like, what is the preferred, stimulus?
Okay, so in the white noise, the STA, for example, when we use the auditory STA,
Mhm.
so what we're doing, we are kind of trying to find what is the preferred frequency on this neuron.
Mhm.
So we're taking the white noise, which has all the possible frequencies.
Mhm.
And then the STA will narrow it down only to preferred frequencies.
Okay.
Is that more clear?
Yes.
Right. And now we must have, if we have this STA, right? So we must get something to read of it from the units that we just added.
Mhm.
So we have two possibilities. Either we divide by the STA or we multiply.
Mhm.
Why is it more relevant to multiply? Because you're kind of saying, I need to narrow down the possible, how do you call it? Activating functions. So I'm saying if this is the activating function of the neuron, is that clear when I say activating function? Then I need to multiply by it. And then why do I divide by the variance? First of all, because I need to get rid of all of the units, right? And second, I'm saying that you need to normalize it by all the possible activation functions. So this is why we divide by the variance, because the variance represent what are all the possible activation functions.
Can I ask something?
Yes, yes.
After you found the optimal kernel with this formula, you have to convolve it with the stimulus to find the estimated rate.
To find the estimated,
The
yes,
this size of,
yes,
and you have to normalize the kernel before convolving it with the stimulus, right?
yes,
So that
But
you
isn't
have
that
to
one-
normalize the kernel.
yes,
So in the end, isn't it the same as STA? Because here you are multiplying
Yeah,
STA by two stars.
but the idea is that now, given any possible stimulus, you can predict the neural response. This is the difference. Do you understand why?
No.
When you have the STA, you're kind of, let's say that you have all the possible functions in the world. And then the STA helps you find what is the preferred function, right?
Yeah.
But then you say, but I don't present the neuron with its preferred one. So how would it respond? So this is the reason why you have to convolve it. You understand?
Yeah, but if you normalize the kernel before convolving, don't you end up with STA? Because
No, the STA is a function of the stimulus.
the STA of the complementary data set.
So this is the PSTH, you mean?
I mean that so you first apply this formula to
Yes.
find the D,
Yes,
but then in the other formula with
here of the,
model,
yes, it's
yes, this one.
above it, yes.
Before doing this convolution, you have to normalize the kernel so that it normal the sum, you have to divide by the sum of the terms within the kernel, right?
Yeah, again, to divide by the sum of,
Normalize it by the
Isn't that only one?
yes,
so that the sum of all values is one. in the
yes, yes.
kernel, no? But isn't it the same as having so if I
No,
take
because you convolve, right? Convolving, one of the things that we'll talk about, when you convolve, it's like filtering the signal. I did not talk about it yet because this is something that we learn in the future. But every convolution is kind of filtering. So when you have this STA that you got from the white noise,
yes.
so this is your filter. So you look at it as a filter of the stimulus. So before the neuron responds to the stimulus, in this model, it first filters it through its activation function, okay? So this is why it's not only using the STA. So two things. First of all, it's not the ST on the model itself, right?
Stimulus of
Is any possible stimulus. It's not only the STA. Okay,
yes, yes.
so this is first of all, it's not only the STA, it's any possible stimulus. So now the function is much wider, but you have to convolve it because based on this theory, the neuron filters the possible stimulus through its preferred or through its activation function.
Yeah, no, I just thought that the D of T is the same as the STA of the white noise. Because after you normalize it,
Yeah.
basically you are reducing it again to.
Ah, yeah, but you need to replace the units. You are asking why not just convolve it just with the STA?
The STA of the white noise.
Yeah, so you must have the units of firing rate of spikes per second, so we must multiply by the firing rate.
Okay.
And then if you convolve it only with the STA, so you're still left with too many units of the stimulus, volt or whatsoever, so you have to get rid of them.
And,
So this is kind of physics idea, that you need to get rid of units, so you multiply and divide by the irrelevant units and multiply by the relevant
Yeah.
units.
yes, yes, it's nostalgia.
Yeah,
And when you perform the normalizing step, if it's dividing by the sum of the elements of the array, then it's not normalizing by rate. It's just normalizing like we have all. these-
yeah, yeah. You need to normalize, okay, anytime that you convolve, you have to normalize, right?
Yes.
I think we talked about it already in the convolution. Yeah, I didn't have a lot of time to go into details in the recitation, but it is written in the recitation notes that you have to normalize each convolution window that you're using, because otherwise it distorts your signals also in the height and not only on the time axis or the x-axis, right? So this is why we normalize.
Yeah, but the steps in the presentation says that we should normalize by rate, so I was expecting the values to be divided by the rate, not by the sum of the.
Yeah.
elements. That's what I don't understand, how do we normalize? Because I would normalize just like this, like dividing by the sum of the elements, but these steps saying that we should do it two finally, that's what I don't understand.
No, I think you're right. It's just normalizing the STA,
Normal.
normalizing, and it's not to the firing rate, but it's normalizing. And maybe what I meant is that you multiply to the firing rate to have this conversion of units.
Okay.
So I think this is the reason why I wrote this line.
Okay, because I think also, sorry,
It's okay.
I think also in the first question, there was a step where the instruction said normalize by the firing rate, and I just divided by the number of firing rate. Is that okay? Or should I do it by the sum?
No, you should do it by the something, the elements, yes. So that the STA will be normalized, yeah.
I think you meant more like convert to parameter.
Yes, probably this is what I should have written. And again, please write me these questions so I can fix it for next year.
We're supposed to multiply the linear kernel by the firing rate. I missed the last part where you said convert it to firing rate.
Yeah, so converting is just like this game with the units, that you multiply by the firing rate and you're dividing by the stimulus units.
So once we have the linear kernel,
Yeah.
we're supposed to multiply, of course, we
You need
normalize
to
it.
normalize it first because
Yeah.
you want to convolve with it, and you don't
Yeah.
want the fact that there are different sizes of the possible STA to affect
Of
your,
course.
right, because,
Normalize the kernel. of the-
exactly.
Okay, but then I don't know why we multiply by the firing rate after.
No, she talked about how we create the linear kernel. We talked about the
Okay, so
formula of creating the.
okay,
Yeah.
sorry, I got confused with, okay,
Yeah.
okay.
I meant it's only a question of units. You multiply and divide only to get back into the firing rate.
In this formula, I think you also asked it here in the presentation. What we need to multiply the mean and firing rate is just a number, right? Not the function, the whole.
No,
function.
no, no, just a number, yeah,
Just the value.
so that the units will be,
Yeah,
right.
I don't know, like, I do remember seeing the R brackets and in my notes, I think, or like in the class. And that said the average of all trials per time. So it was still like a function of time, but of average of all.
It's spikes per second, so it has to be one value.
Yeah, but then like I think in class, it said like one value per unit of time. So like it was still a function of time, but it was an average of all trials. So that's what I was like confused, because then I was like, well, I have this one size
the
of
same size.
yeah, and then this other size.
No.
less, But I can't multiply those.
No, so I think it should be only one number when I'm thinking about it.
Because I was like, I think that would be a little harder, but.
No, not only a little harder, I think that you don't have a model
Uh-huh,
when it is like this, right?
yeah, that's what
As
I.
far as I,
And it's, that's in, the first presentation, but it's a bit different because squared R is just mean firing rate average across triangles. And what I
Yes.
noticed is that you have one triangle, and then you have the firing rate average over this triangle. This will give you one number, right? And then this average, you will average all of the averages of these triangles, and we'll get another
Yeah.
one number. And you can see it like written because if it doesn't have the R parentheses T,
Yeah.
that's not a function, T for the function.
Okay, okay, good. Yes.
Okay, and there is another question here? Christian?
Yes,
Did we answer?
I asked for the S of T, but you said that, so it's the white noise,
Yeah, it doesn't matter. The model should take any given stimulus
uh-huh,
and give you a prediction,
okay,
right? So you can do it either on the main experiment or on the complementary.
okay. Okay, so then, like, I think, I was then,
But as far as I remember, it's really better when you take the complementary.
okay,
It's more accurate.
okay, because then I was kind of confused, I was like, well, then why don't we just take the response to that, like, the white noise as the R model? Like, I was, like, I think I don't, and like, I don't understand exactly, like, what are
Okay.
the steps telling us?
So the R model is your way to say, if I ask myself, how would this neuron respond to any given stimulus? So I want to create a model. And then you want to test the model and to ask yourself, how good is this model? What is the RMSE of the model, of the prediction in relation to the real data? And what is the another possible quantification is the Pearson correlation between them, right? You need to choose what kind of measurement you use in order to yes, to convince us that the model is good.
Mhm. Okay,
Okay, and so this is just about the
so then how would
difference.
like an R model look like if it was a function? Like, is it a function of time, is it a function of stimulus?
it's a function of time, yes.
And like, if it's a function of time, is it?
It's a
how
function
does
of
it know
time
the stimulus?
given the value of the stimulus, right? So let's say you have a vector of stimulus,
Mhm.
you take it into the model, and then you have the model of given the stimulus.
Okay, and then that's what the ST is.
Yes,
Okay.
yes.
Okay. That makes sense now.
So the input is a vector of stimulus, and the
Mhm.
output is the vector of firing rate in time.
So here we would be saying, I'm trying to compare machine learning because you said there's more accuracy with the complementary than the main.
Yeah, as far as I remember, it
It's like
looks,
train and test.
yes.
Okay.
Yes, the idea, it's funny that we always say that it's better first learn the SDA course, because then you have models which are analytics,
Yes.
right? Because you have functions and you want to find the parameters of the functions. So all the Israeli students who came from third year and they did a course about models, so they understand better how to use models in neuroscience. But after some time, the world just went on and said, I don't know what are all the functions of the brain, and I don't know if my models and my functions are good enough. So now I'm going into deep networks and I let the network find the model, while assuming that every function could be approximated by a polynomial, right? Then this is like the Taylor, how is it? Yeah, Taylor sequence, how is it? Theory,
Okay.
right? So it's funny that you took the deep networks before because you have only the predictions, but it evolved after you have the analytic model. And sometimes analytic models are better because they're more explainable, but this is just a scientific question, which we will also speak more about it during the next recitation, because we have like a full recitation only about finding parameters of a model.
Our training set, for example, would be complementary to other set. And
Yeah.
then, you give it, the features, that is the stimulus. for
Exactly.
many.
Yeah, but you don't need deep network for it, right? You don't need to build a network to find the weights and so on,
Yeah.
because this is just using two high canons for a very simple problem, and sometimes you can say more by using a function. Because if the function does predict a lot of the brain behaviors, it is much more applicable to use it. So,
But we can still optimize the parameters. to
Of
that
course.
effective function.
of course, yes.
Because I don't get what parameters we are supposed to optimize in the project.
Yeah, I think I'll just take it off next time. You just need to, you can see it by looking at the data. You don't need to really optimize it.
Like, to get a better, estimate, what
Yeah.
parameter are we supposed to adjust?
I think there is only one parameter of the window size, as far as I
They
remember,
can,
of the kernel, right? But this is a simple kernel.
yeah, because
So-
it doesn't, I don't think it changes.
You don't need to use, I think I'll just take it off next time. I also thought about it in the previous year, that you just, again, using canons for very simple problems.
If it was a very like, variable.
Yeah.
Would not just, a part.
Yeah,
Would it make sense then to try different sizes and see
Yes.
which one gives you a
Yeah.
better estimate?
yes.
Okay.
And I'd probably use a brute force and not like a kind of a network, because it's much easier to debug and understand why it gave what it gave, and there is a higher chance that you are not falling into a local minima.
So we use our MSC.
If you are,
Yeah.
this is again something that we'll speak about it more during the next recitation, but mm, probably brute force would do much better work here.
And then we just report it in RNC, but we don't optimize.
Yeah,
Okay.
exactly.
Yeah, then about this, we're talking about the window size.
Yes.
Resolution.
Uh,
Probably the firing rate.
in the project, as far as I remember, there is the last question in to see that you can optimize the window, right?
Yeah, except there, optimum for the
Yeah,
size of the window.
and now there is a question how you can do it. So
No,
students,
which window are we talking about? Because there is the, to compute the optimal kernel. Okay.
yeah,
You need to compute the firing rate and the STA, right? Or
It's an STA window and there is a linear kernel window. There are two
Yes.
Yeah.
windows.
no, I think this is
The linear kernel.
similar to model of the neuron. No, I think this is just exactly what I told you, to convolve your answer, right?
Yeah, but when you have to optimize it?
Yeah.
Oh, so you're saying. when
So
you say-
after you have the model, you convolve it, okay? Because otherwise it will be too noisy. And you need to optimize the size of the convolution.
Oh, what
like-
is what you told the.
Yes,
Like the parameters of the Gaussian that we choose, for example, if we can model the Gaussian, whatever we wanna.
yeah.
It's
Okay.
not about, this is for the firing it or.
No.
the-
It's for the model. After you have the model, you need to convolve it.
Okay.
What?
Yeah, I'm sorry.
Wait.
Okay, when you have the model,
Uh-huh,
there are many reasons why it gets really noisy, okay?
uh-huh.
And then you need to reduce the noise, so you have the model and you convolve it.
Okay.
And we didn't know that.
You need to-
That's why, okay.
No, this.
It could be just a simple span of a rectangle window, and it could be a Gaussian, and you need to pick. And then I said, you can do whatever optimization you want and just run through all possible sizes of window and all possible Gaussians and so on, and find the most optimal. But to say the truth, this is just too much work to do something really simple. And the window is really simple to find. What is the right window?
That would be like the stimulus, the formula, because we have the R equals.
You, again, here I won't give you an answer because almost every answer will get full points as long as you explain yourself good.
Okay, Because I was also wondering what was the difference between B and C? Because B
So,
says, calculate and plot the optimal kernel,
yeah,
of the neuron assuming linearity. And C says simulate a model of the neuron and optimize the sensitive convolution. So I didn't understand.
no, so the convolution is after the model. Okay, B, calculate. So the optimal kernel is that you just find dt based on the formula that is given. Assuming linearity is because that you don't need to use the static nonlinearity that it's written in the recitation notes, but we also didn't speak about it this year. But anyhow, we don't ask you to add the static nonlinearity, okay? But after you do it, you still need to smooth it. And then you need to find how to smooth it, and you need to explain why did you smooth the way you smooth.
Okay.
Wait, for BB, like you're showing the plot of the linear kernel DT,
Yeah.
right?
Yeah,
And then for C, you're actually showing on model.
yeah.
Is that it?
You will need to smooth the model,
Okay.
and then you need to find yourself what is the best way to smooth it.
Okay, and then for that, like, so like in B8, it says try different window sizes of range, like 100 to 1300.
This one is on the firing rate of the neuron,
Okay,
right?
yeah. So you
So-
get the one that looks
Yeah.
best. Like, is there anything more specific that I should be?
No, hello to science.
Okay.
Yeah, you can choose whatever method to explain yourself.
Okay.
So you can say the thumb rule basically is that you need to take as small as possible window to distort less as possible your data, but still have good enough SNR.
Mhm.
So you can come and say, I'm going to measure the SNR and show that this is the best one for this. This is the minimum window with the best SNR.
Yeah.
Or you can just try different sizes
Mhm.
and write and show that you tried 50, 200, 700,
Mhm.
1000, and so on. And show that this one keeps about the basic pattern of the firing rate. And but it's much less noised.
Mhm.
And the problem with SNR is that you say that it is not fully specific, but this is also true about in science.
Mhm.
Also, when you're going to do your scientific work, and this is why I leave the vagueness over here, because also in real science, there is some vagueness regarding the question, what is the level of noise that you allowed in your in your signal?
And then, do you use that same window that you find for making the STA for the white noise? For the kernel?
No, the one that you made, you mean like after the model?
Because for the kernel, I have it, like, I have a window size.
No, it could be any other window.
Okay,
The one in A is for the firing rate of the neuron. The one in B is for the model. And it's really finding the different parts of the formula. And the one in C is that after you have the formula, you need to convolve it. Can in a minute. Yes,
Still about the section C.
yes.
We are measuring the RNC based on the rates. So in the linear, non-linear Poisson model, the third level part is
Yeah.
spike generation.
Yes.
Here we are not. We don't need.
No, you don't need to create this to do the spike generator because it is enough to show the firing rate and the firing rate of the model. No need to show the spikes themselves.
Okay.
If you want, you can, but you don't have
Yeah, I
to.
was trying that, but the optimization should be done on
Right.
the firing rate side.
Yeah.
Okay.
And it is really hard to do it on the Spice
Yeah,
because there is a level of stochasticity.
yeah.
Stochasticity.
So that's more for
So-
like modeling than for the like finding
Yeah.
the best function.
Yeah, yeah. So for example, if you have a brain stimulation that you have the electric current, you probably want to do it as the neuron does. So therefore you need the spike generator, but your model could be good enough just for example, LFP or whatever.
Okay, thank you.
Yeah,
When we are optimizing PC,
yes,
so let's say we choose Gaussian window.
mhm,
And we have to optimize the size of this Gaussian.
yes,
Okay, so we choose different sizes and then we.
yeah. So this is called the brute force. Brute force, that means that you take all possibilities and you just try one after the other. And then you can evaluate which was the better one. So if you had 10 options, you find the best one. And another possibility is that I say you don't have to use brute force. You can use any model for optimization, including deep networks if you want to find the best size. And another possibility that you can also have full points for it is just by explaining really good your answer without really calculating. You can also, so the reason I left it like this is that you can still just explain, I tried this and this and this, not all the possible windows, but 5 different. And then I saw that this window does a very good, good enough work, and the RMSE is very, very low. For example, you found out that 50 is good enough, and there is no difference between 50 and 75 in the RMSE. So this is, you will get full points. Okay? Okay, this was a nice question. Yes.
Oh, sorry. I'm still a little bit confused how we evaluate the window and also in regards to like
Okay, so if I want to be as strict as possible, I will just tell you, take all possible sizes of the window from 0 to 2000, okay? And then try each number, 0, 1, 2, 3, and so on. Just try all of them and calculate for each one the RMSE and stick to the one which the RMSE is the lowest. This is called the brute force.
mhm.
So calculating all the options from a given range of window size.
Okay. Yeah.
I wrote here that you can say, I want also to use a simple rectifier. You can also add a simple rectifier if you want to try it. And I wrote here that you can use any optimization that you wish. I highly recommend if you want to be strict, so do it with brute force, but you can also just try different sizes of windows until you find the one that looks for you the best. And of course, you need to calculate the RMSE, okay? And you can say, okay, you can see that it is almost about the same. There is not a lot of shift. It gives almost the same as the one that was in A, okay?
Mhm.
So this is why I
so
said you don't have to optimize the model to its best. You don't really need to find only one solution. You can have only a very basic. Try 10 different numbers of windows and just find which one is the best. Okay, did I answer, Aylan?
Okay. Yeah.
can I ask a question? When we
Yes.
need to optimize the size of the window, does it mean the window that we use when we build the STA?
Here in C,
Yes.
no. In C, after you have the model, you need to smooth it, to convolve it. And you
Okay.
need to decide what is the window that you convolve it with and what is the size of the window.
Okay.
And as I said, it should be the smallest as possible because you don't want to distort too much. And, but you still need to think. Some of the windows will just keep it very, very noisy.
Okay, thank you.
Okay, great. Okay, more questions?
Yeah,
Um,
so it's a linear, rectifier.
Yes,
How do we use it?
you multiply the R model that you have, you just multiply it by the rectifier. Therefore, what is the idea of the rectifier is that you say there is a basic threshold of activity that this neuron needs to be above it. So you kind of say, okay, if the stimulus was under 10 volts or whatsoever, now you need to add in a rectifier that says don't fire at all if there is if it is less than this threshold.
So maybe it's just a scalar, a number.
Yeah, but you need to take it from when you look at the stimulus function.
Yeah.
There is no need to take a rectifier of 10 when all values are above 100.
Yes.
So you need to pick a possible value from the function and try to add it. Maybe it will make your model more accurate.
Just like a filter.
A rectifier is not a filter. It's a nonlinear function. It's like kind of cutting your function and saying this function does not start from 0 to 100. It starts from 3 to 100.
What are the units?
So a rectifier will take the stimulus, for example, and you can either rectify the stimulus and say if it's under than 10, don't even put it in the model, or you can rectify the full model and say this neuron could not have a negative firing rate or less than 5 spikes per second firing rate. Okay, so you either add it on the stimulus or on the full model. Okay. It's okay. I'll finish with her because it will be in Hebrew. So.
Just asking about actually, we already answered the question for the
Is it here, by the way, your question?
Oh, no. It's
Okay,
not. I'm
okay.
just like asking about how I submitted because for example, for the first question, right, that we have to generate the spike trend, right? So if this is how I zoom in already.
Yes.
But if I do not zoom in and use the whole scale of 90 seconds, it's gonna be like that.
No, so you don't need, you're asking about the first second, no, zoom in.
Okay, just zoom in and screenshot it.
Yeah, but the main thing that we check is more of the autocorrelation
Okay.
and so on, so.
All right, thank you.
You're welcome. By the way, how much to zoom in? So that we still see that this is not a regular neuron, or you understand that we can see that it is stochastic. Okay, so not too much so that there will be only 5 spikes, but not too many. Yeah.
Thank you.
And another possibility, by the way, is just to take a few parts of your code and to show the first 100 millisecond and the milliseconds between 1 second and 2 seconds or something like that.
All right.
Take a few parts.
All right. Thank you.
You're welcome.
Okay, so I still have a question about what Irene asked. That when maybe she showed you, I don't know, but when we check the model on the first the main experiment, okay, so we get this noisy,
Right.
we can convolve it, and that's I understand. And but you know the stimulus itself, like the actual firing rate, that's what you get.
So
It's very strange.
so that means that also the firing rate is not convolved, right? It should not look like this, the firing rate.
But if you convolve this, what will you get?
So maybe you have all these peaks, so even if you have a small convolution,
Oh, maybe the window size is too small.
yeah,
appropriately. Okay, and you
it
said
should be about this trace that you see here, there is like a kind of a trend. So you'll see about the same trend both in the model and in the firing rate.
I understand that, but I tried more than one, window size options and they just, it looks very strange. I mean,
Maybe the windows are very, very small.
Hmm?
The window size, shouldn't it be like in the number of bins? Try
Um,
10, for example.
This takes a little longer, yes. Okay. What is this? Like it looks like.
Okay, so you
very
have a
strange,
problem of bins.
Okay.
There is a problem with your convolution because it should be really smooth, but now you can see the trend.
Mhm.
So the problem before was that you took a very, very small windows.
Okay, so if I.
And now it looks like something here is not really convolving because they kind of look binned. Do you remember in the first
Yeah, but I
project?
didn't use the Gaussian. Like, should I use?
No, I don't
Doesn't
know if
matter.
no, it doesn't matter. It looks like something is not really, maybe the
Okay, I'll
convolution
check
is not in a step of one bin each time. Maybe, for example, it's here and then it jumps here and here, so there are two,
I'll check.
the jumps are just too big.
But
This
you
is
said-
what I would suspect.
Okay, but you said we can also do it for the complementary experiment,
Yes,
right?
yes,
We can check on
Yes.
that.
yes.
Okay.
But this looks better than the one that you showed before,
Yeah.
because here you see the trends.
Yeah, so I'll try to fix it.
I
Now-
think it's just the jumps.
I'll check.
So instead of just jumping one
Mhm.
index each time, I think it jumps more.
Okay, no, just.
One last one.
Yes, yes, it's okay.
One last thing. Do we expect that the estimated rate is way longer than our actual neuron?
So there is a problem with the convolution because the convolution makes it longer.
Okay,
So maybe you need to assign in the function itself that it needs to keep the same size as was before.
but even if I
and-
do not say.
Yeah, so there's a problem here. I don't know why you didn't take this. But you see that the fact that you have this, this means that it is not the same size, right?
Okay,
Because this is just about the zero padding, you see in the end of convolutions.
okay, so there's something wrong, okay,
Yeah,
okay,
so I would try to take something like.
okay.
Sometimes can you show me what convol? Yeah, it's convolve. Go to the numpy and check what is going on over there. Maybe you need equal and not same. I don't
Okay.
fully remember.
Okay, okay. Thank you so much.
You're welcome.
Thank you.
Okay. I'm going to Hebrew. I hope it's okay.
Can I ask
And
one last?
yes, Ailan, yes.
Maybe it was already asked. I was just wondering in question 2, in B, I
Yeah,
don't understand how you find the best window size. I'm confused by this question somehow. Yeah.
so you try, again, the question is how do you estimate what is best? You don't have a very good answer.
Mm,
You just need to have something that you still see the trends,
mhm.
but you don't lose too much information.
So,
So I'm
Okay.
sorry, you can either measure it and have an SNR measurement, but this is just a bit too much. So you just need to check possible different window sizes and choose the one that you think is the best. I'm sorry for not giving you better answer
no,
because
yeah.
there is none.
Yeah, no, thank you. Okay, and in terms of the window, we're relatively free, like, because it says like we should choose one that is suitable for a linear
Yes,
current model.
yes, yes.
But-
And you need to say, I tried this, and this was too noisy, and then I tried this, and this was too smoothing. And so I picked the one that looked this and this, and you will have full points. So just.
Okay, I will try. Okay.
Okay.
Yeah, thank
Great.
you. Thanks.
אוקיי, אביה, את מחוברת גם. אוקיי.
בטח אני טוב, לפחות 8 פעמים.
לא, זה בסדר.
בשאלה 2, בקטע, קודם כל הבא, שאמרת אני צריך חלום.
כן, כן, זה בדיוק מה שאמרתי.
לא הבנתי.
אנחנו מדברים על זה, נכון? בין 100 ל-1,300.
כן. לא הבנתי כל כך מה כתבת בקבוצה שקונבולוציה עם הקרמל כאילו...
נועה חשבה שזה בעצם כאילו אין צורך לעשות קונבולוציה גם כאן וגם כאן וגם כאן, כי במילא אנחנו בסוף נעשה קונבולוציה עם הקרנל, עם ה-DT, זה קונבולוציה, נכון?
אני כאילו, אני פשוט עשיתי כאילו גדלים, את הגדלים שביקשתם, דיברתי קרנלים בגדלים האלה, ועשיתי קונבולוציה עם הפעלים.
לא, אז זהו, את צריכה קודם לעשות עם פיילים את הקונבולוציה, כי צריכה לייצר קונבולציה פיילים. כשאתה מייצר, כשיש לך ספייק טרן, ואתה מייצר ממנו פיילים זה, אתה חייב לעשות קונבולוציה, נכון?
אוקיי.
אז את צריכה לבחור מהו חלון הקונבולוציה.
שזה החלון שאני מנסה?
כן.
אז מה זה הקרנל?
הקרנל, זה בעצם השלב הבא. הקרנל זה כבר המודל שלה.
אוקיי.
אז המודל שלך אומר את הדבר הבא, אני אשב ואני אציע לך עבור כל גירוי באשר הוא, מה יהיה קצב הירי של הנוירון.
אוקיי, אז כאילו אני קודם כל מחליקה את הקצב ירי כדי שיהיה פחות רועש, ואז...
נכון, ואז מתוך זה את מוצאת את מוצאת את הקרנל שלך, שמה זה הקרנל? הוא עושה לך את הטרנספורמציה מגירוי לקצב ירי. נכון? יש לך פה גירוי, את רוצה להגיע לפונקציה של קצב ירי.
כן, זה עשיתי לפי המספר, כאילו של המספר.
מעולה.
אבל עשיתי את זה ב-B, כאילו שטיפה...
נכון, כן, אז אין בעיה, אבל הדרך שאת מחשבת אותו,
אבל בוא אני...
כן, בדיוק, את משתמשת בקצב הירי הממוצע, שזה נלקח מתוך פונקציית קצב הירי.
אוקיי, אז נחפש את הקרנל עצמו. איך אני יודעת באיזה חלון להשתמש?
תנסי, זה לא משנה.
זה לא משנה?
זה לא
כאילו,
משנה.
איך אני יודעת מה זה משנה?
תראי, יהיה חלון מסוים שכבר לא תקבלי שום דבר הבדל, כשתעשי את ה-STA.
כאילו, אני רוצה שיהיה כמה שיותר קטן.
פשוט תסתכלי מה, את צריכה כאילו את החלון שנותן לך את האינפורמציה מלאה. תקחי גדול מדי, אז לא יראו את זה בכלל, תקחי קטן מדי, זה יהיה רק חלק. אז הייתי מנסה עד שאני, כאילו, העניין הוא למצוא מה זה ה-STA, מהו הגירוי שהנוירון מגיב אליו, כאילו הגירוי המועדף על הנוירון. אז יש נוירונים שעבורם, זה יהיה גירוי של דקה, יש נוירונים שעבורם, זה 100 מילישניים. את צריכה לראות מה זה הנוירון הזה. אז ב-C אני פשוט אומרת את הדבר הבא, יצרת את המודל, את תקבלי מודל מאוד מאוד רועש. מה שעכשיו את צריכה לעשות למודל, את צריכה להחליק אותו, כדי שתוכלי להשוות ביניהם. איך להחליק, באיזה אופן, את צריכה להחליק. בנוסף, מה שאני הצעתי, אם את רוצה לשפר את המודל שלך, יכול להיות שצריכה להכניס non-linearity, החלטה שלכם אם אתם רוצים למצוא את זה. אז non-linearity זה אומר שאחרי שיש לך את המודל הזה, את כופלת את המודל, נגיד ברקטיפייר, זאת אומרת, אם קצב הירי הוא מתחת ל3 ספייקים לשנייה, תעשה את זה כאילו זה 0, זה רקטיפייר. זה מה? בדיוק, רלו זה רקטיפייר, כן, זה כאילו זה הראשית הזאת. רקטיפייר ליניאר משהו.
זה בקשר לאחד. כאילו לכם את השאלה צריך להציג את כל הפיגרים, שיראו אותם.
אחלה.
כן, ואז עשיתי כל חפים נפרד כדי ש...
זה נראה לי מאוד יפה.
כן?
כן. לא הייתי מטרדת מזה. אנחנו רגילים לקרוא מאמרים שיש להם.
זהו, זה פשוט ממש לא רואה את הצירים.
לא, זה נראה לי בסדר גמור. את יכולה קצת להגדיל את הכותרות שלי, קצת יותר קריאה.
פשוט זה לעשות את זה.
לא, תעשי את זה כתבתי לך, תעבדי פאורפוינט.
כן, אבל את הכותרות עשיתי בפייפון.
אז תשימי, את מעתיקה את זה לפאורפוינט, או אפילו כאן בוורד, את שמה את הכותרת, כאילו, את שמה, אל תסתבכי. תעשי אינסרט.
כאילו לעשות את זה.
כן, וכאילו תדרסי, מה זה משנה? וגם להריץ את זה שוב, גם עשיתם את זה כאילו...
לא, להריץ, שהוא
דקה.
מעתיק עוד פעם את כל
הבנתי, לא, אז פשוט
הריץ
תשימי הכל טוב.
ושאלה כללית, אמרתי תרגול שרואים, השקעתי בפרק.
ממש, הייתי קוראת את המאמר שלה.
כן, כן,
תגיד.
באמת השקעתי.
אני רואה,
אמרת בתרגול שרואים משהו בהזארד שלא אמרתי קורלציה.
כן, בהזארד, גם אם יש לך נוירון פואסוני, אז לא תהיה לו את העלייה הזאת. אוטוקורלציה, הרבה פעמים אומרים אוטוקורלציה ישרה, זה חלק מהביקורת כאילו שאני מצפה שאתם תנסו אולי להביא לכם. אוטוקורלציה, אם זה קו ישר, זה אומר שזה פואסון, זה מה שבדרך כלל נגיד.
אבל לא שומעים כאילו את התקופה הרפרקטורית.
נכון, אבל גם כשיש לך תקופה רפרקטורית, אז יש לך את הקרניים האלה, נכון? כן, וזה לא קיים בהזארד. אז כאילו, אוטוקורלציה, אם יש בה קו ישר, אז אולי כן יש כאילו התנהגות פרסמת, אבל גם לא בהכרח, אבל ההזארד נותנת עוד מידע. אז כאילו יכולים למצוא, למשל, כן, בדיוק. אז כאילו אני יכולה לשבת ולהגיד, תראו, אתם מדברים רק על אוטוקורלציה, בפועל יש עוד רצון פרסונית, אפשר לתת את ההזארד, ואז לנסות לנתח איזה מידע, אם היו מסתכלים על ההזארד, נגיד, שוב, ברמה ביקורת כללית, רעיונית, לא צריך, לא להריץ סימולציות ולא זה, אפשר קצת להתייחס למה שעשית כאן, ואז להראות שכאילו לפי אני חושבת, ממה שאני קראתי, לפי השיטה שהם מציעים, הם כל כך סטריקט, שהנה, יש לך פה נוירונים פואסוניים, אבל הם פשוט לא היו מתייחסים לזה כאלה פואסוניים. אז הייתי אומרת את זה, אז זאת הכוונה. וכן, שתראו שאפילו מאמרים כאילו שיוצאים, בסדר. כן, זה נוירון פואסוני. אז אמור לתת לך. תראי, הם כולם פואסונים.
כן,
סבבה. אז זה לא חד משמעי. נכון. נכון, והסיבי, אני רואה שיש לך גדולים, שזה מעולה.